So next up, I would like to introduce Dr. Brian Helmuth. Dr. Helmuth is a professor at the Marine Science Center at Northeastern University in Boston, holding a joint appointment in the Department of Marine and Environmental Sciences and the School of Public Policy and Urban Affairs. Helmuth's research and teaching focus on predicting the likely ecological impacts of climate change on coastal ecosystems and on the development of products that are scientifically accurate, understandable, and useful by a diverse array of stakeholders. In 2001, he was named a Google Science Communication Fellow in the area of climate change. He also served as a lead author on the technical document for the inaugural Oceans chapter of the United States National Climate Assessment. Please join me in welcoming Dr. Brian Helmuth.
Thank you very much for that. A few years ago, I was speaking to a journalist about what I do for a living, and he said, so really what you're doing is you're triaging a train wreck. You're looking at damage that is being done, and you're trying to figure out what we do about it. And that analogy really stuck with me. As I want to get into, what we try to focus on in my lab is how do we understand climate change enough to do something about it? We're definitely at the point where we have plenty of information to act. There are a lot of unknowns, but there's definitely enough information for us to make proactive change. And this idea, this analogy of a train wreck works in several ways. First of all, climate change is already underway. As you heard from Nigella, we are committed to change. The question is not if we're committed to change, it's how much. We're already seeing impacts on ocean ecosystems around the world, as Nigella outlined. Even if we magically cut off all greenhouse gas emissions right now, and we're showing no signs of doing that, there's still inertia in that system. So just as you think about inertia in a train wreck, those trains are going to continue to go forward even if we put on the brakes. Every time we make predictions through the IPCC about what emissions are going to be like, we always exceed those. So if you look at those worst case scenarios that come out every year, I think it's probably even a little bit worse than that. So the point is we're committed to change. We're committed to a change of at least a degree. We're committed to ocean acidification. We're committed to sea level rise. The question is how much, and can we stop that train? Can we stop that before we hit very dangerous levels? So the way I kind of think about this is there are two things we can do. Doing nothing is not an option. Denial is not an option if we want to survive this. Rather, first of all, we have to put the brakes on the train. That's mitigation. We have to stop what's driving that train forward into the train wreck. And second of all, we have to prepare for oncoming change. We have to adapt to what the future is likely to bring. And this is a stupid biologist view of business, speaking in the business school, but the way I kind of think about this is if we're looking at mitigation, we have a longer term return on our investment, but it's a much higher return. So any changes we make today are going to be benefited, our children and grandchildren will be benefited many more times than we will today. So essentially we're investing in our children and grandchildren's future. Adaptation, in contrast, is investing in today's society as well as tomorrow's society. So it's admitting that right now we've got impacts of climate change going on. We're going to continue to have Hurricane Sandys. We're going to continue to have droughts. We're going to continue to have these problems. What do we do about it? And so obviously we need both. What I want to talk to you about today is how we can use science, my form of science, to address some of these questions. And in particular, I want to talk about a field called ecological forecasting. A lot of my work is funded by NASA and the National Science Foundation. So we take very detailed forecasts of weather and climate, use that to understand biological responses at very small scales, and then take that back up to look at what those impacts are likely to be at the ecosystem level and to people, and ask, how do we change that? How do we change our future productively? So I want to give you kind of three examples, both from my own work and also from the work of others, to kind of illustrate what I think we can do looking forward in terms of climate adaptation. The first, as you heard and we'll hear much more about, is aquaculture. Really, we can't continue to rely on wild-caught harvest. If you think of the way fishing works, it's the last wild-caught industry on Earth. It's the equivalent of us going out and hunting deer on a grand scale. So we really do have to look for alternatives to this. Farmers have known for millennia that different species respond differently to different environmental conditions. We can use that information productively to ask, if we're trying to start, for example, an aquaculture operation at one location on the shore, what animal should that be? Should we use mussels? Should we use oysters? What strain of those should we use? We can take our knowledge of biology to inform shell fisheries. So for example, differential stress amongst mussels and oysters. Another example is marine spatial planning. Nigella again spoke about marine spatial planning and how marine protected areas really are a good way to preserve ecosystems, even when we don't understand a lot about how they function. Just leaving them alone in some cases really can be beneficial. However, that being said, this goes back to this idea of triage. We're already seeing damage, and we're already seeing damage to an extent that there are some places that really we're not going to be able to save. This is a controversial idea because it really says that we are triaging. We are putting black toe tags on some locations. We all know that funding is always limited, political will is always limited, political capital is always limited for doing these kind of things. So let's just imagine that we have 5 sites, all potentially subject to stress from climate change. And I have to always put out the disclaimer, these are really big stars, so don't take any of these sites literally. I've gotten in trouble before for saying which ones are damned and which ones are not. They're all potentially subject to stress from climate change, but also from these other stressors. And again, a point that came out in Nigella's talk is that whenever we consider climate change, we have to consider it within the context of these other stressors. Climate change is often the trigger that fires the bullet. And so seldom is climate change acting alone on these organisms. When we overfish populations down to a very small size, that makes them much more susceptible to climate change. When we hit organisms with pollution and increased temperature, that makes them much more susceptible to die. So imagine in this scenario, we only have funding to create one marine protected reserve. Where are we going to place it? Well, if it turns out that we put it someplace, we expend all our political capital, we expend funds to put it someplace where no matter what we do, 20 years down the line, that site is going to die, I would argue that we've thrown good money after bad. We really could have done much better with that funding. So ideally, what we really want to do is we want to identify the place that is healthiest, not only now, but in the future, 20 years in the future, as far in the future as we can look, 50 years, and really invest in that area. That can then serve as a seed bank for other surrounding populations. We see these spillover effects, for example, where you'll see a line of fishers lining up around a protected area, and that's where they catch the really big fish. We do give low priority to sites where really, frankly, at this point, there's nothing we can do about it. And if anybody's from Los Angeles, again, don't take this too personally. This last one, though, is where it's the most interesting to me, and it goes back to this idea that climate change is a stress multiplier. I think the U.S. Department of Defense really has it right, but they call climate change a threat multiplier. Really, that's what we're talking about here. Climate change almost never acts alone. The problem is it's taking all the existing problems we have and it's making them 10 times worse. It's making them that much worse. So when we're dealing with climate change, we're not only talking about mitigation, about reducing temperatures, reducing OA, but also these other stressors. And it's this final part that, say we don't have enough money left over for a protected area, but we do have money to reduce one of these other stressors. So we may put in a campaign to reduce sediment runoff or pollution or overharvesting. Even if we can't locally affect the climate, if we can't affect temperature, we can affect these non-climatic stressors and prevent those populations from going over the edge. And so it's identifying not only the good ones, the bad ones, but also these kind of marginal populations that I think is really an area where we can make some headway. The final example is early warning systems. As I'm sure you all know, there's uncertainty not that climate change is happening. There's uncertainty about exactly what will happen in the future. And the longer we look into the future, the more uncertain that future becomes. A lot of that is because we don't know what greenhouse gas emissions will be, but this is a complex system. I mean, there's no question that greenhouse gases are leading to climate change today. That has been known since the Civil War. I mean, you look at the back of the envelope calculations that were done in the 1860s, they're surprisingly close to what we see today. So this is not new to science. But there always are going to be surprises, and so any strategy we have to build in some flexibility to account for the fact that there is something we've missed or conditions will be very different. And I think the Gulf of Maine in 2012 is a great example of that. If you look at the temperatures in the Gulf of Maine in 2012, the temperatures were 1 to 3 degrees C higher than the average climatology. So think about what that means. When we talk about we're expecting a 1 or 2 degree increase in the next 100 years, we've already exceeded that. This is a graph that shows in blue the climatology, the average temperature between 1982 and 2011. These are the temperatures in 2012. So early on in the spring, we saw this big spike. We saw this temperature increase. The Gulf of Maine is warming faster than 99% of the large bodies of water on Earth. The end result was we had this boom in lobster production. Lobsters respond to temperature like other organisms. They went through more molts, they grew faster. The way this works is the US fishers start fishing the stock before the Canadian fishers do. So the US lobstermen went out there, caught record amounts of lobster well before the Canadians could catch them, and we became flooded with lobster tails that continued on for years after that. There was a big international debate because the US lobstermen got the lobsters before the Canadians did. This was all predictable, and this is taken from an article by Mills in 2013, where she argues that, look, we have enough information. We know how lobsters respond to temperature. We saw early on in the season what those temperatures were. We really could have predicted this. What the limitation was that we didn't have a flexible enough strategy to deal with that. We didn't have a regulatory framework that would allow that. We didn't have backups for lobster fishermen who may have been able to switch to a different stock, which also gets into the issues of gear. But the idea here is that we can develop these early warning systems. And so it's these protecting the environment now and in the future based on what we know about science that I really kind of want to spend the next couple minutes getting into. Before I do that, though, there are 3 points that I think get lost in this discussion frequently. The first is that, by definition, global climate change is a global phenomenon, but the impacts are going to vary really largely from place to place. As you saw in the previous slide, what was going on here in New England definitely was not diagnostic of what was going on in California, for example, where there's a severe drought. The other important point is that species all respond differently to these environmental stressors. They respond differently to temperature, to ocean acidification, to pollution, so that climate change is likely to lead to winners and losers. Often those winners are things that we don't like. They're things with broad tolerances like mosquitoes and disease organisms. And a lot of the things we do like are particularly sensitive, like corals. And then this third part is that it's often hard for us to predict where the trouble spots are likely to emerge just from a human viewpoint. We have, as I'll show you in a minute, a very biased view of how the world works from our kind of human perspective. So just to back in another version of this map, this shows a temperature anomaly on the surface of the globe. And we can see that it's really all over the place. We see places that have been cooling. We see temperatures that have increased in some cases in the polar regions by 9 degrees Fahrenheit in the last 50 years alone. But the point is there's a huge amount of variability in the amount of warming over the surface of the globe. So often when we talk about this is a 1 degree C increase in global average surface temperature. What that means is that on average, by far, most of the sites around the world are heating up, but not all are, and certainly not in magnitude. We see the greatest changes at the poles. And that's important because if you're a barnacle sitting on a rock, if you are a wheat plant, if you are a frog sitting in a tree, you could care less what the climatology is. You could care less what is going on even 100 miles away from you. You care about what your immediate environment is. You care if it's too hot around you to live or die. You care about whether it leads to reproductive failure or not. So this gets into where we often have this kind of misconception about the difference between weather and climate. Where climate by definition is a 30-year trend in weather. So when we look at a 30-year trend in weather, that doesn't mean that if it is colder next year than it is this year, that climate change isn't real. Just as if it's warmer next year than it is this year, doesn't mean that climate change is real. It's a long-term trend in weather conditions. This is a very useful metric because if we look, for example, at an average difference in global surface temperature of today in 6 degrees, that's the difference between now and the last ice age. That's what we're predicting with fair likelihood by the year 2100 in the opposite direction. So think about the magnitude of the difference between now and the last ice age and the opposite direction of what that might look like in 2100. But really, as a biologist, what we care about is not climate per se, it's we care about weather. And so the way that to think about this is Deke Arndt and Noah kind of came up with this analogy, is that it's climate that trains the weather, but it's weather that throws the punches. And I've learned after giving this talk a couple times that there are a number of people that have not heard of Brockie, they've not seen Brockie. So to put it in other terms, this is climate, this is weather, this is what Tampa Bay feared last night, is going to fear tonight. And so this is what we need to figure out based on this. Second point is that there are these winners and losers. Organisms all vary in their physiological responses. Things that have broad tolerances, as I said, are things that we tend to not like. And this is nothing new. I mean, this has been known to farmers for generations and generations, that warmer and wetter is good for some plants, but not others. So I just have this is a report on climate change that the USDA put out, looking at the optimal temperature for reproduction, for growth, et cetera. These are all things that we can measure. We can measure these things for any organism on Earth if we have enough resources to do that. And it tells us something very useful. So for example, these are changes in 3 fish stocks on the east coast of the US, 3 species of hake: silver hake, red hake, and spotted hake. This is from the year 1968 to 1980, and this is through 2008. You can see a general northward shift in the populations in the silver hake and red hake, with pretty much no response at all from the spotted hake. They could really care less what happened to the temperatures. So all living in the same area, all species of hake, but they have very different responses, in large part likely due to their physiological tolerances. So this is the kind of information we use in my lab group. We take weather data, we take what are called reanalyzed data, where we take weather data from buoys, from satellites, from weather stations, and then we put those all together to get complete global coverage. We turn that through a series of custom sensors and models into estimates of how hot organisms are. We then ask what are the implications for survival and what are the socioeconomic consequences. So why this gets tricky is that 99% of all organisms on Earth are ectotherms. We make our own heat. The vast majority of other organisms get most of their heat from the surrounding air and on land from the sun. So this is just an infrared picture. If anybody's seen like Predator or a cops video where they're looking for pot growers, this is the same kind of camera that you use. These are 2 animals sitting right next to each other, a predator and a prey, a sea star and its prey, and they have really different body temperatures because of the way they interact with their surrounding environment. So I won't get into a lot of the details, but really we use basic Newtonian physics, but for heat. We look at how heat moves in and out of organisms. We use heat budget models. We also build custom sensors. Discover Magazine did an article on this when Wall-E came out and started calling them robomuscles. We have these things around the world. So just as the shape and the color of an organism affect how much heat is absorbed by its body, the same thing applies to sensors. Why this is important is when we stick these custom designed sensors out in the field, we get differences between air temperature or an unmodified logger of up to 14 degrees C. So an absolutely huge difference when we put these loggers out. And what it shows us is that our human perceptions of where trouble spots are likely to emerge are often faulty. We really can't rely on what we think of as common sense. So this just shows a graph of the maximum temperatures along the west coast of the US, and it points to the importance of local environmental factors. In this case, is when low tide occurs in the middle of the day, but you can think of the same thing in tree lines where there is rainfall occurring, changing the vulnerability of organisms. We can use that information to make predictions into the future. So this is a project we did with University of Palermo in Sicily, looking at vulnerability of aquaculture species of mussels. And what this allowed us to ask is not only what are the current limits to distribution of these commercial species, this is a species of Mytilus, a mussel, but also what's the role of food? If we have increased eutrophication, is it going to be a good thing or a bad thing? It turns out in a couple of these places, a little bit of increase in food due to increased runoff is actually really good. It can counteract some of the effects of temperature increase by increasing food supply slightly. So this is information that we can provide to aquaculture managers, to people who are concerned about what's going to happen at a very local scale. So just to kind of wrap up, as hopefully I've emphasized, I mean, climate change is here. It's already happening. So what I would argue is that the role of science is no longer to determine if climate change is having an impact on organisms, on ocean life. We know that it is. There are plenty of examples that it's happening. What I'd argue is that really the goal that we ought to focus on is figuring out what species are most vulnerable, where are they most likely to be vulnerable, and what do we do about it. And given that information, armed with that information, I think we can proactively prepare for a lot of these changes. We won't be able to prevent all of the changes. It's definitely not going to be a panacea, but it will at least allow us to look forward in a proactive way rather than just wringing our hands and hoping for the best. And with that, I'll stop. Thanks.